Welcome to AP Environmental Science. In this video, we are going to talk a little bit about global wind patterns and what causes them and the directions that they travel. Now, first, we need to understand a few properties that determine these air circulation patterns, and they're air density, water vapor capacity, adiabatic heating and cooling, and latent heat release. And we'll go through each of these one at a time. The first one is air density, and this just follows the basic principle that warm air is less dense, and that means that warm air will rise, cold air is more dense, so cold air will sink. The second property is water vapor capacity, and this means that warm air can hold more moisture or humidity than cold air. In fact, the term relative humidity is a measure of the actual water vapor that's present at a given temperature compared to what that air could hold. So in the summertime, you've probably heard what our relative humidity is on each given day, especially on those hot days in the middle of summer. Now, saturation point is the amount of water vapor that can be held in the air before it starts to rain or precipitate. Now, if you look at the images at the bottom of the screen, you can see that the 90-degree Fahrenheit image has a much higher water vapor capacity than the 40-degree Fahrenheit image. This means if you spread that amount of water vapor throughout the entire atmospheric column, the colder temperature has a much lower relative humidity than the warm temperature. And if you look at the graph in the top right-hand corner of the screen, you can see the general trend of water vapor capacity, where the maximum amount of moisture that the air can hold significantly increases as the temperature increases. The third property is adiabatic heating and adiabatic cooling. Now, adiabatic processes, these describe how that temperature changes in the atmosphere as a result of changes in the amount of pressure. So in adiabatic heating, as the air pressure increases, and this happens as air moves closer or falls closer to the surface of the Earth, these molecules are going to become closer together, and that will cause there to be more friction between the atmospheric molecules. Now, as a result of this increased friction, there is going to be an increase in heat, so that air is going to warm. The opposite is adiabatic cooling. So this means as the air moves further away from the surface of the Earth, that air pressure will decrease. That means there's less friction between those molecules because there's less volume that they're being squeezed into, and that means that there is going to be a decrease in heat, or the air is going to actually cool. So these two processes play a pretty key role when describing this phenomena called a Hadley cell, and we'll get into that in a little bit. The fourth and final property that you need to know is called latent heat release. And this is just the release of heat energy in the form of heat as that water vapor condenses from that gaseous phase to the liquid phase as they condense in clouds and then fall out as precipitation. Now we can put all of these pieces together to describe what's called a Hadley cell. And these Hadley cells are convection currents that cycle between the equator and approximately 30 degrees north of the equator, and between the equator and approximately 30 degrees south of the equator. Convection currents are the same type of phenomena that helps to move tectonic plates within the crust of the Earth. So this just means that they're driven by heat. So the first step is that the equator experiences the most direct sunlight. And that means that at the equator, that sunlight is heating that air closest to the equator. It's going to warm, and that warm air will rise and expand. Now, air that is rising and expanding, it will start to cool due to that adiabatic cooling. And in the process, as that air is cooler, it's not able to hold as much water vapor and moisture, so we're going to have a whole bunch of precipitation taking place over the tropics. Now, that cool, dry air that's high up in the atmosphere is going to get pushed away from the equator because there's more air rising up in the middle, and it will move to about 30 degrees north and 30 degrees south, where it will begin to descend towards the surface. Now, as that air descends, it's going to start to warm due to adiabatic heating. So it's going to become more dense, and that is going to increase the friction and increase that heat. Now, once that warm, dry air is near the surface, it's going to be pulled back towards the equator, again, because that air at the equator is being driven up into the atmosphere. So this Hadley cell is this loop or this convection current that is ultimately driven by the intense solar radiation that the Earth receives at the equator. Now, a term that you need to know is called this intertropical convergence zone. And this is that zone where the most intense sunlight is found on the Earth. And this is kind of a wavy line right around near the equator. This is an image of a Hadley cell, and you should pause the video and write this down into your notebook. You can see as the air warms at the equator, it's going to rise, it's going to experience that adiabatic cooling, and it will release its moisture through precipitation. Then that air will be pushed towards 30 degrees north and 30 degrees south, where it's going to sink back towards the Earth and warm up. That is why we find deserts right around 30 degrees north and 30 degrees south of the equator. And that's dry air is going to be pulled back towards the equator as this whole pump or convection currents continues to move. Now we can see that these Hadley cells take place driven at the equator, but they are not the only convection current in our atmosphere. In fact, each hemisphere actually has 3 convection currents. And we have these Hadley cells near the equator, we have these polar cells near the poles, and in between them we have these ferrel cells. Now the Hadley cells and the polar cells are driven by heat, whereas this ferrel cell is just kind of this gear that's being driven and being pulled because of these other 2 cells. And this actually drives a lot of our prevailing winds throughout the Earth. The Coriolis effect actually plays a pretty significant role in determining the direction of weather patterns throughout the Earth. Now, the Coriolis effect is this phenomena that causes the deflection of an object's path, and this is due to the rotation of the Earth. So imagine you were standing at the North Pole and you threw a ball directly towards the equator, and you could throw a ball all the way to the equator. Now that ball would not travel in a straight line. In fact, it would curve just a little bit towards the west. Same thing if you were standing at the South Pole and you threw a ball to the north. It would actually curve just a little bit to the west as well. But we have some interesting phenomena where if you were standing in the northern hemisphere and threw a ball towards the North Pole, it would actually deflect a little bit to the east. So we're going to talk a little bit about that here in just a moment. So if the Earth did not rotate, these convection cells would move air directly to the north and directly to the south. We wouldn't have these weather patterns in the United States that move from the western part of the country towards the east. If it was just the Hadley cells, the ferrel cells, and the polar cells, our weather would move from the south to the north and from the north to the south only. But because we have the Coriolis effect, we have our weather moving from the west to the east and from the east to the west. So if we look at this, as the solar energy hits the equator, it drives that Hadley cell, and that air that's moving from 30 degrees north back to the equator, that is being slightly deflected to the west instead of moving directly south. So that is the reason why we have these northeast trade winds blowing towards the equator in the northern hemisphere. With the ferrel cells just to the north of the Hadley cells, we have the general pull of the air is from the south up towards the north. And if we had no rotation of the Earth, that would be the direction of our weather patterns going from the south to the north. But we know that that's not the case from living in the United States. We know that we have these westerlies that are moving our general weather patterns from the west to the east. And that's again because if you stood in the northern hemisphere and tried to throw a ball directly to the north, it would curve slightly to the east, and that slightly eastward curve is what drives these westerlies, which are our major wind pattern in the northern hemisphere, particularly in the United States. Now, in summary, you need to be able to explain how environmental factors can result in atmospheric circulation. You need to remember that the most intense solar radiation is at the equator, particularly along the ITCZ. You need to be able to understand and explain Hadley cells, along with briefly a little bit about ferrel cells and polar cells, particularly explaining how they are related to and driven by adiabatic heating and cooling. You also need to know the direction of global wind currents and their association with the Coriolis effect. I know this was quick. Please send me your questions, and I hope that as you watch this video, you were able to learn something.